Right, good morning, guys. Before we go into our next lesson on solving differential equations, I do want to review with you on differentiating a natural log function and then integrating a function that involves a natural log function. Because we do need to know these skills to progress further into our unit. So these are a couple of just basic examples, and we're just going to go through the derivative formula. Okay, so we're differentiating. So y prime. All right, so the derivative of a natural log function, just sort of as a formula, is 1 over u times u prime, right? So in our first example, the u value is the 3x minus 1. Right? So the derivative would be 1 over 3x minus 1 times the derivative of 3x minus 1, which is 3. So that would lead us to a final answer of 3 over 3x minus 1. Okay? Number 2, just do the same process. So y prime would be 1 over x squared minus 1 times the derivative of our u value itself, which would be 2x. And that would lead us to a final answer of 2x over x squared minus 1. All right, so there's something really important to notice about how our derivatives look. The tough part about recognizing that you're going to be involving a natural log function with antiderivatives, well, the problem is that, the ln disappears in the antiderivative. It's not like we see ln here or ln here. But there is a very special relationship that both of these fractions share. And that is the relationship of the degrees of the numerator and denominator. Degree would mean the highest exponent. So notice in this answer, the degree of the denominator was 2, the highest exponent seen on x. And here, the degree was 1. Okay, so notice that relationship. Over here, the degree of the denominator was 1, the highest exponent we see on x. And the degree of a constant is 0. And that's really because any constant could technically have x to the 0, right next to it. So the relationship that I want you to see is that in both situations when we found the derivative of our natural log function, in the final answer, the denominator has a degree that is 1 larger. Here, same thing. The denominator has a degree that is 1 larger, right? That's really, really important in recognizing when you're going to incorporate natural log functions with integration, right? So now we're going to change our thought process, and now we're going to go back to integration, right? So we're going to integrate. Let's see, we're going to integrate 2 over, 3x minus 1, okay? And then we would have to look at this and try to figure out what to do with this. And I want you to notice the degrees. The degree of our denominator is 1, and the degree of our numerator is 0. So notice that the degree of the denominator is 1 larger than that of the numerator. So it's the same relationship that we spoke over here, right? So remember, when you're integrating, this really represents the derivative itself, right? So we're basically given answers that look like this, right? So once we see this, we're gonna realize that the answer to this question is the ln of something. Now, if you consider what the original function looks like, it's the ln of the u, right? Now, what's the u value in this case? Well, let's use our previous examples on derivatives to help us see where the u value is. For number one, in the original function, this is where our u value was located. And check it out in the derivative. This is where our u value is located. Right? Even in number two, look at where the u value in the original function is located, and look where it showed up in the derivative, right? So we actually know a little bit about what the original function looked like. The original function, again, because of the degree relationship that we see here, one larger in the denominator, it comes from a natural log function, and the u value is really the denominator. Right? And then we have a little plus c here. But very similar to yesterday's lesson when we were trying to find the antiderivative of an exponential function with a base of e, I encouraged you to do a check. You shouldn't be satisfied that this is the full correct answer. So we have to understand that this, to us, represents the original function. And this, to us, represents the derivative of that original function. And if we go ahead and find the derivative, which again should look like this, we are going to be a little bit off. 1 over u times u prime. And of course, the derivative of a constant is 0. So that final derivative as of right now looks like this, which is not a direct match to what we want our derivative to be, right? So very similar to what we did yesterday, you have to think in terms of multiplication. By what factor are you off by? So basically, what should we multiply this current answer by so that we can achieve what our goal is? And this is a little trickier because it does involve a fraction here. We want this 3 to go away and become a 2. So check it out. How about if we actually multiply by 2/3? Wouldn't that be the case, right? The 3's would sort of cross-reduce down, and then you would be left with 2 over 3x minus 1. That's the number that our original educated guess was off by of our antiderivative. Right? So we're going to do another practice example just like this. Okay. And how about we do, let's do 2x over 3x squared plus 1. Okay, so again, looking at this, we would notice the relationship of the degrees of our numerator and denominator. So here we have a degree of 1, here we have a degree of 2. So we have that relationship that we spoke of before. The degree of the denominator is 1 larger than that of the numerator. So right away, we want to recognize that the antiderivative is going to be that of a natural log, right? Okay. So we know that this derivative came from the natural log of something, right? So where is the u value? Well, the u value, as we saw in all of the previous examples, right? The u value was the denominator of our derivative, right? Same thing here. Okay. Notice that the numerator, the 3, didn't show up in the original problem. Notice the 2x here didn't show up in the original problem. It's the denominator of the derivative that's crucial. Okay, same thing down here. Our denominator was 3x minus 1. Check out what that u value is, right? So we're going to follow that same relationship. And we're going to understand that the u value is here. Okay? But then we're going to be very careful. And we're going to say, I'm not satisfied that this is the perfect answer. And we're going to check, right? Currently, we are suggesting that this is the original function, right? And we know that this right here is supposed to represent our y prime. So let's see if we're spot on or if we do have to adjust this answer a little bit. So the derivative of a natural log function is 1 over u times the derivative of u, which would be 6x. And of course, the derivative of any constant would be 0, so that would be dropping out. So if we clean up our derivative, again, we will notice that we do not have a direct match. We're very close, but it's not perfect. So that means that our original anticipated antiderivative is off by some sort of factor, right? So we have to ask ourselves, what can we multiply this by so that we can achieve 2x over 3x squared plus 1, right? So basically, we have to turn this 6 into a 2. And we can easily do that if we multiply by 1/3, right? If you think about it, if you multiply by 1/3, this 3 would cross-reduce with this 6, and we would get the 2x that we need. The 3x squared plus 1 would be untouched. So that is what our antiderivative is off by. Okay? So for today's lesson, I'm not going to move us forward until tomorrow with solving the differential equations. What I'm going to do is I'm going to post some homework questions, and you are going to submit them via Edmodo, just as I did yesterday.